Good day. I am Engineer Ezekiel Magbanua and I will be presenting a technical paper review for power electronics. So we'll start with the introduction and paper overview. So the title of the paper is BYD Blade Battery for Sustainable Mobility. So this is a technical, economical, and environmental review. So the authors are A. Megalingam, N.P. Hariram, and K. Sadhakar. So this is a journal regarding energy storage and saving. So the publication year is 2026. So the current status of this paper is journal pre-proof. Now, we'll proceed to the engineering problems tackled by this paper. So it focuses on more on the conventional Li-ion limitations. So first, the safety vulnerabilities of the batteries of electric vehicle. To be specific, the BYD battery. Then the resource constraints of the battery-related challenges. Then the performance trade-off. So these are the three main engineering problem tackled by this document, and I will try to focus on to them and explain them further on the succeeding slides. Next, so the study has three research objectives and an analytical framework. The first one is the integrated multi-dimensional evaluation. So that's the first. Second, structural and thermal validation. Third, sustainability and scalability mapping. So again, this is all um, related to the BYD Blade Battery, which is, I believe, a very new technology for BYD. The initial the initial version of the BYD battery, as I've reviewed the document, is in 2020, and the version 2 was March 2026. So they only have two versions so far of the BYD battery. So we'll be tackling this furthermore on the analysis later. Next. So these are the scope of the analysis. Of course, the BYD blade architecture. So the first one we'll be tackling later, the technical specification of the battery, then the economic and market feasibility of this technology, of course, if it's really economical and strategic for the users of BYD to convert or to upgrade with this type of battery. Then the third one is the life cycle and ecological footprint. So we'll be tackling the environmental impact of the technology. Next, so these are the key findings of the paper. So far, it focuses on to the longevity of the battery and also the environmental impact of the technology. So the first one is that it has achieved more than 3,000 complete charge discharge cycle. So it's a superior lifespan with negligible capacity delay. So it is equivalent to a total of 750 miles of distance traveled with a single life of the battery system. So that's for the longevity so far. Then we have on the environmental impact, 70% reduction in life cycle carbon footprint. And this is achieved when the cell to pack setup integrate with renewable heavy electrical grids. So that's more on because the battery composition later that I'll be discussing is that it has less type of chemicals that requires or are rare. That's the term for it. The second part is that for the environmental impact is that it has 0% cobalt composition and also the nickel composition. So that's it for its findings so far. So we'll go into the comparison first. So for the BYD Blade Battery with chemical composition of lithium iron phosphate, so LiFePO4 or LFP, so that's how it's defined. So it can withstand up to 500 degrees Celsius of working temperature. With, of course, for the nail penetration test, it has zero ignition or smoke, even though, again, it was penetrated or it has a hole on it to one of its cells. It has zero ignition rather. Then for the production cost, it is optimized with 21% of net cost savings. Then for the spatial utilization, it enhances 50% because of the cell to pack mounting compared to the traditional chemistries that we have, the NMC and NCA. So I just want to highlight here one of the I think amazing thing is that for a nail penetration test, your BYD Blade battery doesn't ignite or smoke compared to the catastrophic failure and ignition of our traditional chemistries of electric vehicle batteries. So that's it. Then also one of the critical limitations and trade-offs of BYD Blade battery is that at freezing temperature, so the efficiency degrades by 20 to 30%. So this means that it has to be heated when charging at very low temperature. Then, of course, the cell two pack paradox. So this is one of the problems that they have. If you want to replace a single cell, the cell to pack architecture doesn't allow you to do so. So it requires a complete pack replacement. So this is because of the 20 megapascal adhesive that holds the whole system. So I'll explain it later further, hopefully in the later further discussion. The next is the electrical engineering analysis. So we are here now. We'll go through the battery chemistry, which is the lithium iron phosphate or LiFePO4. So again, it is cobalt-free design. So cobalt and nickel are we know rare um sorry, excuse rare chemicals and elements that requires rigorous processing. But again, the composition of this chemistry, which is I believe very innovative, only requires lithium, iron, and phosphate, which are common and abundant types of chemicals that we have. Next is the electrochemical stability. So it has an active cathode feature with strong covalent bonds that allows for easier um, charging and discharging of the system. Next is it has a degradation resistance, which is a minimal structural capacity degradation over tens of thousands of microscopic charge discharge cycle. That's why it achieved more than 3,000 charge and discharge cycle. Next, so we are on the cell to pack architecture, which is we're just showing you the diagram in contrast with the traditional modular layout. So as you can see for the TML or the traditional modular layout, it requires space. But then for the cell to pack architecture of the BYD Blade battery, it becomes part of the structure that is load bearing. So it basically can carry weight and adds rigidity to the structure of your electric vehicle, which is amazing and innovative. And it has also easier dissipation of heat or easier management for your byproduct heat because of its wide surface area and overall how it is shaped. So that's how would I describe the cell to pack architecture. Next, so for the battery management system or the BMS concept, so this is also an advantage with the BYD Blade battery because it has first equalization controls. It mitigates cell to cell variations, voltage, and SOC across the prolonged blade array. So basically, you don't pressurize, or you don't put electrical pressure when charging to a specific cell only. So it distributes, it balances the whole system, the whole pack. Next, it has safety integration, which actively monitors electrical signatures, safeguarding against overcharging, over-discharging, and cell degradations. It has a real-time monitoring when running, when being charged, and when at rest. So that's the advantage of the BMS processor. Then, of course, it has an active system that incorporates advanced equalization and also balances energy distribution and enhances efficiency and overall extends its lifespan. Next. Now, this is just for a comparison on its efficiency and energy and life cycle performance. So it has a gravimetric energy density with a rating of 140 to 160 watt hour per kilogram. So it basically outweighs or outperforms the traditional NMC batteries that we have, which lower rating for this metric. Then again, it has very long life cycle capacity of more than 3,000 full charge and discharge cycle. And then in real world mileage, it can, without accident, of course, you can go a distance of 750 miles. So that's how long the battery can stand, provided that you don't experience, or it won't experience an incident causing damage to the battery. Then, because of the cell to pack architecture, you have a volume penalty erased, because again, the pack itself, the group of cell becomes part of the load bearing structure of the system. Next, for the charging and thermal management, so you have um, basically this is one of the challenge being faced by the BYD Blade battery during temperature, or at temperature below -10 degrees Celsius. It drops from 20 to 30 degrees. This necessitates integrated preheating system because um, I believe this is because of the um, chemistry, or the chemical that being charged, because you only have lithium iron phosphate and it requires heating. If it's, I believe it has a negative temperature coefficient that requires preheating at lower temperature. But it has thermal advantages, specifically compared to conventional cylinder type batteries. So the flat blades has easier way of what you call this, trying to put away heat, because again of its flat shape, and the heat dissipation is advanced by 30 to 50%. And of course, because of the architecture, you are also saving space. It becomes load bearing and adds rigidity to the system. So you have lesser thermal management required for the system, and it becomes part of the structure that carries weight. Then of course you save space. That's it. Then for the battery safety and thermal, sorry, I can't read because of excuse me, doc, thermal runaway. So the BYD Blade Life PO4 has really an advantage because it can work well on a limit of 500 degrees Celsius. So that's amazing for the BYD Blade battery. Again, this is because of its chemical composition and how you pack it, or package the chemical compared to the conventional NMC. Then for the nail penetration test result, it is amazing and advanced to have no ignition, explosion, or smoke, even though there is a hole on a single cell that is part of the pack. Next, so these are just the comparison of your BYD Blade battery compared to the NMC, NCA, sodium ion and the expensive solid state batteries that we have. So there are trade-offs, but then again, because of the BYD battery, BYD Blade Battery chemical composition, it is um the composition is not rare, I say, and can be acquired because again it's just lithium, iron, and phosphate compared to cobalt and nickel, which we have political issues on acquiring that type of chemical. And it has also again advantages on the thermal runaway limit, also on the life cycle, uh, energy density, but I'm not looking into the solid state, and that is costly. But of course, the commercial status of this one is widely available, so that's what we are looking into. Next, the applications I'll be mentioning it. So electric vehicles, smart grids, and renewable integration, and heavy duty uh, energy storage. So next on the engineering impact and sustainability. So it has specialized production. I believe this is the challenge, of course, because the manufacturing facility of BYD is limited. And as for the countries that creates this, of course, challenging architecture. So it's limited. That's for the challenge. Then for the integration, so you have the strategy of controlling everything from raw chemistry to CTP integration. So that's their strategy to achieve uniform, consistent output. And of course, industrial automation. So this is the QC solution, which skips modules and removes thousands of wires bond, requires highly synchronized, high current electrochemical impedance testing to catch internal parameter drift early. So these are the considerations and the challenges for the production of your BYD Blade battery. Next, of course, the cost and life cycle implications. Because of the advantage of your cell-to-pack architecture, again, it becomes a load-bearing structure with the diagram there, and this saves space. At the same time, it also gives you a stable olivine structure that delivers 3,000 to 5,000 full charge discharge cycles, which of course you maintain 70% original capacity after prolonged cycle. So after that, you still have 70% of its original capacity. So the operational pack stretches beyond 10 years. That's still amazing. Knowing that your electric vehicles, some of the electric vehicles are encountering problems right now. Next, for the environmental sustainability, so I'd like to explain that very quickly that your BYD Blade battery is nickel free and cobalt free. So again, it reduces your carbon footprint production and also is economical in the sense that your chemical composition are readily accessible. Next, so these are one of the again battery recycling and end of life. So because your cell to pack architecture won't allow you to remove a single cell, so the whole pack should be removed. So the echelon use or the second life purpose of your BYD Blade battery can be used in lesser equipment like lesser torque requirement motors or even storage for energy storage for your solar PVs or at the residential or other industrial applications that require lower electrical pressure. Next, it can also be used in renewable energy integration because of um, the volatile input of your variable renewable energy. So the BYD Blade battery can also be integrated to the system with let's say a 100 megawatt hour installation. So the edge again of your architecture, BYD cell to pack architecture is that it's load bearing, and it can also because of its equalization advantage, the BMS system, it can carry um although rough and volatile input into smoothly injected power output at your grid. Next, for of course, it's sustainable transportation because of your cell to pack architecture or cell to body frameworks. So you save a lot of space for this one, and it can also be later on applied to your mass transit or heavy freight industrial equipment. Next, so we are on the engineering critical review. So I'll just go through with this one. So I believe it will be quick. So forces at play. So you have chemistry and architecture trade-off matrix. So that's just how we are going to compare it. Again, this is another comparison of your cell-to-pack architecture to your traditional NMC and CA. So again, it's very advantageous and innovative. Next, so the blade beam structure diagram. So this is amazing also. This is one of the advantage and highlights of your blade battery. So because of its architecture and structure, so you have easier way of heat dissipation, and at the same time, you have a strong, rigid battery that can carry weight. Next, so these are the blind spots and also the analysis and gaps of your BYD Blade battery. So I'll just I won't go through each of them, but I'd like to get at least one or discuss one, which is the first one, the homogeneous thermal distribution. So this is it overlooks localized microspots near internal tabs. So that's one of the assumption of the authors. So the missing analysis here is the lack of electrochemical impedance spectroscopy, EIS profile. So that's one of the requirement for you to have a homogeneous thermal distribution, a monitoring system that has rigorous way of checking hotspots. Then the research gap for this one is, of course, missing thermal mechanical strain coupling models. So that's one of the research gap, and hoping in the near future it will be tackled and studied. Next, so for the recommendation for the future researchers, of course, the advanced BMS, diagnostic integration, dynamic active balancing topologies, and probably, although expensive, the solid state co-design architectures will be made in the near future. So we are on the conclusion. So far, these are my the notes I've taken. So for 5.1, so this is one of the important notes I have taken, is that packaging can be or can give a powerful impact to the system. It's an innovation, and there's a lot of advantage because of the how you package it, how you form the chemicals. Second, it has the decoupling constraints. So the CTB design allows battery to perform dual load bearing and electrochemical tasks. No compromise on um, its power capacity, but you have an advantage onto the load bearing system. Then the aspect ratio management, it's also relevant to electrical engineering in the sense that it is a module-free strings that demands highly precise SOC or SOH algorithms. So it has to have a real-time monitoring for your SOC and SOH. Then it has high power dynamics, megawatt scale, 8C um, regimes that requires intense internal resistance modeling. So I won't discuss the C, but it talks about the capacity to charge. So we have 1C, 2C, 3C, etc. So hopefully we can discuss it in the near future. Then the grid interface integration. So it has large arrays, demands transient stability analysis, and high voltage DC to DC conversion. So the synthesis for this paper is that the mechanical packaging innovation directly dictates the operational boundaries of power electronics and BMS design. Then these are again for future potential industrial applications. You have automotive sector, industrial marine and automated handling, then grid scale energy storage system. So far, I'd like this evaluation to be short. So I'll go into the overall recommendation. So the target audience is essential for power system engineers, battery researchers, and electric powertrain designers. And it has, um, I'd like to say this, that this must be read alongside supplementary impedance or supplementary literature covering electrochemical impedance, spectroscopy, and automated recycling framework to obtain a fully balanced technical review. I believe this ends my presentation. Thank you so much for listening, and I'll end this presentation. Thank you.